Can you see the screen?
Yes, sir.
All right. Okay. All right. So, is this clear? What we did last time? Yeah. So, equation of the plane. Equation of the plane which is tangent to a graph. Is this clear? Yeah. So now, so how many of you have found this A and B? Yeah. Did anybody try to find A and B? So let us a little bit repeat little bit what we wanted to do. So we wanted to do. So we wanted to find a linear transformation. We wanted to find an analog of the linear transformation so h goes to f prime a times h in real variable in one variable. Analog of this one in of course analog of this one this is in one variable in our case. So this is the linear transformation lambda from R to R. Well, f is given to be R to R differentiable such that limit h tends to 0 f of a plus h minus fa minus lambda h by h norm. So norm is just modulus here is 0. Right? Right? This is the linear transformation. This is the linear transformation. Is it fine? Yeah. Now we want to find the analog. We want to find the linear transformation analog to this one in our case. In our case means we have considered a function f from R to R. Right? And you want to find the relation. So what does this lambda has to do with this tangent space? This tangent space. Right? So this is one, and second, what does or what is the relation between the tangent space, tangent plane to the graph x y, f of x y, right? In R3, and the linear transformation lambda from R2 to R that represent the derivative. Right? So this is the question. Right? Is the question clear? So what is the candidate for lambda here? Do you have a candidate in mind? Anybody?
So can you repeat what is the?
What is a candidate for this one lambda? Or rather, what is a guess?
Sir, the graph represents the linear transformation. If we
Graph does not.
if we shift the point f of x comma y to 0, that means
Mhm.
if we like if we take x is equal to a, y is equal to b, and f of a comma b, and shift, then we get the tangent and shift the point a comma b and f of a comma b to origin, then we get a linear map in R2 to R that represents a linear map. So this may be somehow related to lambda.
But this is actually not true, right? So you have this graph something like this. If you whatever which way, so you have, suppose you have a ball, right? You have a soccer ball, and wherever you move by translation, it will remain a soccer ball, right? It cannot be a plane, right? So soccer ball is not a graph. That might be your argument. Okay, so make it half. Now you can see this as a graph. So half of the soccer ball, upper half. This can be seen as a graph. Now wherever you move, you cannot flat it, right? Just by moving here and there. So the point is, you need to look at the tangent space. This one, you need to find the equation of this plane, and this plane has something to do with the derivative. Just in case of one variable, let me show you in case of one variable. So in case of one variable, what was it? So, x-axis, this is y-axis, and you have some graph, something like this, x comma fx, and it, yeah, anybody want to speak? So now you look at the tangent. Look at the tangent at one point. Now, what is the equation of this tangent? Let's say a, and this is f of a. So, what is the equation of this tangent? We told it last time.
Y, yeah, y is equal to f of a plus uh, f f dash a into x minus a.
It goes to into x minus a. All right. So this is it. So now this is the line. So this is the equation of the tangent line of the graph at a comma fa is this. Now look at this one. So if x is near to a, if x is near to a, you can put x minus a as h. So what you get is y equal to f of a plus f prime a times h, right? So here you get the linear transformation, right? Yeah. So here you get the linear transformation that represents the derivative. Yeah, all right. Makes sense. So it is expected that once we find the equation of the plane passing through x naught, y naught, z naught, where z naught is f of x naught, y naught. So that means once we find a and b, then perhaps we can get the linear transformation in terms of this one, right? That could be a candidate, isn't it? Yeah. So this part could be a candidate. Okay, let us try to see that. So now the equation of the tangent plane or the plane passing through, or it's not actually the plane, it's an equation of a plane through the point x naught, y naught, f of x naught, y naught, right? So this is the point. This is the point which we are considering here. So let me copy this part. Right. So this is the point. So z naught here is sorry, z naught here is f of x naught, y naught, right? Is this fine? So the equation, what is the equation of the plane passing through this one is z equal to f of x naught, y naught plus a times x minus x naught plus b times y minus y naught. So equation of the plane, of course, which is not vertical. Which is not vertical. Right? So you know a general equation. So this plane, this could be the equation here depending on a and b. This could be a plane something like this. Something like this. Or it might be a plane of this form. Depending on the equation. This could be, so it is a general equation passing through this point. Now we need to find conditions where under which this will become the tangent, right, of this graph, of this graph. All right. So here we need to look at. So we now need to look at the partial derivatives of f at x naught y naught. All right. So the partial derivative is important now. So you are actually going back to one variable and then try to understand. But of course, we assumed that there exists a linear transformation. That part is important. Lambda exists. That part is important. We have assumed that. Now to compute lambda, we are actually taking help. We need to take help of the partial derivative. So what are the partial derivatives? So let's look at the point here. Let's look at the thing as follows. Yeah. So this one, this corresponds to some point here. Say this one, x naught comma y naught in xy plane, right? So these are the general equation. So we are not actually interested in there as such. We are interested in the red plane only. All right. So, all right. So z naught is f of x naught y naught. We are interested to find this one. We need to look at partial derivatives. Now, what are partial derivatives? Let us try to understand again. I have done it once. Now let's look at. If you look at a line like this, passing through x naught y naught, parallel to x-axis. All right. Now corresponding to the this one, the image will be something like image could be something like this, right? So now if you look at the tangent to, so there will be this image of this line. What will be the image of this line? It's a curve, right? Now if you look at the derivative, so this, now look at this line. So try to think of this as a real line. So here in this line, y equal to y naught, right? So we are considering the function x goes to f of x comma y naught, right? This is a one variable function, and it is also differentiable. Now x is varying here, y naught is fixed. So what you get as derivative is the slope of this tangent line. Fine? Is it understandable? So the derivative of this function the derivative of this function at x naught, x equal to x naught, is the partial derivative del f by del x at x naught y naught. Is this clear, everybody? So this becomes one variable function, this becomes one variable function, so this should be, derivative of this one should be slope of a tangent. Tangent to what? Tangent to its graph, and its graph is this one, this line. Graph is this line, so tangent will be this one, the slope of the tangent will be this, right? All right. Similarly, one can see the function as similarly we can consider the function y goes to f of x naught comma y. So you can also consider a line which is parallel to y-axis. This is x equal to x naught, and here it will be something like this, and tangent will be like this, right? And in this case, so you get, similarly you can consider the function here and its derivative at, oh, so this is right, so this is x naught comma y, its derivative is del f by, derivative at y equal to y naught is del f by del y at x naught y naught. So is this clear? Any question till now? The partial derivatives, the interpretation of partial derivative. Okay. Anyway, let's continue. Now, so we have this partial derivative. So what is the relation between this partial derivatives with this partial derivatives and the lambda? Right. So the point is, you see this partial derivatives, this since it is this plane is touching in the circle, this plane is touching to the surface, or you want this plane to touch in the circle, so better be this line inside the plane. All right, it should be there. So if you consider another function, something like this, so if you define this two function, define g x y to be f of x naught y naught plus a x minus x naught plus b y minus y naught. And then look at the graph of g. So graph of so the graph of g is the plane drawn above. Right. So the graph of g is this plane. Right. So now what we actually want is as follows. So touching, so this plane touches the surface would mean, so the graph of g touches the graph of f means that del f by del x at x naught y naught is equal to del g by del x at x naught y naught, and del f by del y at x naught y naught equal to del g by del x del y at x naught y naught. And this was A and this was B. So the equation of the tangent plane to the graph of f from R2 to R is z equal to f of x naught y naught plus del f by del x at x minus x naught, oh sorry, x naught comma y naught times x minus x naught plus del f by del y x naught y naught. Write it down here. Del f by del y at x naught y naught y minus y naught. All right. So this is the tangent, equation of the tangent. This is important. All right. So and this is the analog of. So this is the right analog of this one. Right analog of this one. Right. So now we can put this.
So,
Yes.
the way we derive the del f's, we basically took a cross section and then we took the tangents along those cross sections, and then we said these two tangents must lie on the plane.
Must have.
But the two cross sections that we took were x naught comma y and x comma y naught. We could have
Right.
taken any other cross sections passing through x naught comma y naught as well, right?
Yeah.
Any
Yeah,
other
yeah.
line passing. So
Definitely.
these del f's are definitely not anything special. Just they are easy to calculate, right? That's why we include del f's. Huh?
Exactly. So these are just one variable. You are looking at one variable function and taking derivative. So del f easy to del f by del x, del f by del y. These are easy to calculate. Absolutely right. And you could have taken any line. So you could have taken any line, but the point is, then it will not be del f by del x and del f by del y. That will be different one. So that will come later. So we'll consider those directions as well. But here, these are two particular directions which are actually giving you a one variable function. Right? if you look at any other line, it will not be of one variable function all the time. Or maybe it may be one variable function here. Here it will be depending on, of course, x not equal to some x equal to some m times y, right? So it will depend on both of them, but yeah, ultimately it will be of one variable. But then this will not have this particular expression. So we want to find this a and b. So this a and b will not be determined by other direction. So it is likely for the time being, and we don't know about the other directions also. We have not studied that. Those are called directional derivatives. So here, looking this particular lines which are parallel to x-axis and parallel to y-axis, we are actually looking at the function as one variable and then compute the derivative, which we get the partial derivatives, and then this, by condition of the plane touches to the graph, we will get a and b, right? And at any other direction you take, the vector will the tangent line will always be lying in the plane. Definitely, that is true. Yeah. Any other question here?
Sir, we have looked at an example that function is defined as xy by x square plus y square. So the property was that this function is not continuous at 0 comma 0, but the function has the partial derivative at I think the partial derivative was defined.
Yeah, partial derivative
Yeah, so now
exists.
if we just think of this in this context, so that means that the function, there is not a particular continuity at 0 comma 0, but we can get a tangent plane at 0 comma 0. So like it's intuitively, I mean, I feel little bit confused, because like then
Yeah,
what point touches at 0 comma 0 to the tangent plane?
right. So look at this example in one variable. Right. So this is a graph, right? Isn't it a graph?
Yeah.
Yeah. So what is the tangent at this point? So what is the tangent at this point?
Actually, it is not differentiable at this point. So like if we go from the left hand side, so there will be one kind of tangent, and the tangent will change if we arrive at this point from the right hand side, I think.
Right. So you get this tangent. This is also a tangent, and this is also a tangent, right?
Yes.
Both of them. So so if you look at that, the function you are referring to, fxy equal to xy by x square plus y square, it will have this type of property. You might get several planes, not one plane, because at this point function even not defined. So instead of let's say this you remove this point and put it value here, right? This could be possible, but still
Okay.
tangent exists.
Yeah. So we have to like the plane depends on which side we are approaching the point.
Right. So this is actually one plane, right? One plane. But this is actually one plane. When f is differentiable, this plane is actually the tangent plane. If it is not differentiable, the graph, then this might represent one such thing, right?
Okay, sir.
Yeah, not exactly. So it will be zero here. See here, the derivative in your case, what happens? This is zero. This will also be zero at 0, 0. So what you get is the constant plane. So something like this. Yeah, well, I should mention this one also, right? This also touches. At one point. But the point is, of course, it is not differentiable. So this is not, this kind of planes are not unique. So differentiability actually gives you the uniqueness. So you can check that this one, what happens in your example. All right.
Okay, sir.
Okay. So check that, you'll find this part only, which means it's parallel to xy plane. All right. Now let's next look at what is the relation between this and the linear transformation lambda, right? So we assumed a from R to R is differentiable, right? Differentiable, let's say at x naught y naught. That means there exists a linear transformation lambda from R2 to R such that limit h tends to 0, or I should write little bit elaborately. So let us write it as h comma k tends to 0, which is in R2, f of let's say a comma b plus h. So I could write it to understand better. B plus k minus f of ab minus lambda of h comma k is norm, which is just modulus norm of h comma k is equal to 0, right? We know this limit exists. Now let us play with this limit. So choose our direction. So suppose k is identically 0, and we look at k is identically 0. So look at the limit h tends to 0, norm of f of a plus h comma b minus f of ab minus lambda of h comma 0, right? Norm of h comma 0. This is equal to 0. Now h is in R, right? By this limit, since this limit 1 exists. So let's call this 1 in 1. So this implies limit h tends to 0, f of a plus h comma b minus f of ab minus lambda 1 comma 0 h, right? Lambda is a linear transformation by, what is this? This is nothing but h, right? Is 0. So this means limit h tends to 0, f of a plus h comma b minus f of ab by h is lambda 1 comma 0. Lambda at 1 comma 0. Lambda was a linear transformation, and this 1 comma 0 is the standard standard basis of R2, right? Yeah. And what is this? What is this? The whole thing? Yeah. By definition, what is this?
Did you
Partial
ask me?
derivative of x at a.
Right. Del f by del x at AB. Right. I choose A comma B. Sorry, I must have chosen this X naught Y naught. Yeah, X naught Y naught. 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 This is at X naught Y naught. Right? So this is the relation you get from for with the linear transformation lambda and the partial derivatives. Right? Similarly, taking k equal to h equal to 0, we get that del f by del y at x naught y naught is lambda 0 comma 1. All right. So see the relation. So lambda of h comma k is nothing but del f by del x at x naught y naught h plus del f by del y at x naught y naught k, right? And which is nothing but coming from here, right? This one. See? And that is the relation between tangent plane and the derivative, right? So we get generalization of the slope, right? The slope is not there anymore, but you have something. You get a linear transformation, that's that part, and you get the same thing here. Right? Is this clear? It's an example. So example we'll take is this one. Let's say fxy equal to 2x plus y square and y plus x square. Right? So what is the derivative lambda? What is lambda? See, there is a catch here. We assumed lambda exists, then we found this form. We assumed lambda exists, then we found this form. So here you can guess by using this procedure, this part, but to prove you actually need the existence of lambda. So you have to show the existence of lambda before we go forward, right? So there is a catch here. That part we need to look at. That one we'll look at next time. So here you do it by hand. So you consider f of, let's say, what is that lambda at 0 0. Okay, which is lambda is nothing but df at 0 0. So first of all, you have to have f to be differentiable, right? So you write f of h comma k minus f of 0 0. This is 2h plus k square comma k plus h square minus 0 0. Right? Now this is nothing but same as 2h plus k square k plus h square. Right? Now, so you first need to guess, right? So we need to find, we need to show that there exists lambda r2 to r such linear such that f of h comma k minus f00 minus lambda h comma k not norm by norm of h comma k limit h comma k tends to 0 must be 0, right? So you need to guess lambda. So my guess. So what is your guess? Let me ask you. So what is your guess lambda? A candidate for lambda. So what is your guess? Anybody? Nobody have any guess? Well, that's pretty surprising that nobody has any guess. So see, lambda is
2h plus k. 2h plus k.
2h comma k. So
Yeah,
lambda, you should be taking, you must be guessing this one as lambda. So 2h comma k. So 2h comma k would be 1. So which means like hk go to 2h comma k. Let's try this. So that could be a candidate, possible candidate. If that doesn't work, then the problem is complicated. So let's try that. Limit hk tends to 0. f of hk, so that is known, so which is 2h plus k square k plus h square minus f00 is 0. So lambda is 2h comma k by norm of h comma k. So this is limit hk tends to k tends to 0. This one you need to write. So what is this? This is c. 2h gets cancelled. 2h gets cancelled. K gets cancelled. So we have just k square h square. So this is k square h square and norm of h k. Right. So now you have to remove the norm. So let's say h k tends to 0, and here we look at square root h to the power 4 plus k to the power 4 by square root h square plus k square. Yeah. So how do you prove? So what will be the limit of this?
0.
Yeah, was that so?
The term in the numerator is proportional to, like, in some sense proportional to root over x to the power 4. So it's around the order 2, and in denominator it's root over x square, so it's around order 1. So the
Yeah,
numerator goes faster to 0 than the denominator, so it will go to
right. But in mathematics, you need to give precise argument. So you first see that this is a positive quantity. So you give an upper bound first of all. So square root of h to the power 4 plus k to the power 4 by square root of h square plus k square. This is greater or equal to 0, and give you an upper bound. Now in upper bound, you just put a simple one, h square k square 2, h square plus k square, right? Yeah, you've added one more term here, 2h square k square. So this is bigger, less equal to here. So this means here h square plus k square whole square, h square plus k square. So which is square root of h square plus k square. Now take limit both sides. Take limit. What is happening? Take limit as hk tends to 0 to get limit hk tends to 0 root over h to the power 4 plus k to the power 4 root over h square plus k square is lesser equal to limit hk tends to 0 h square plus k square, and this is 0, right? So you get the limit to be 0. So hence we get derivative of f at 0 0 is, of course, at h comma k you need h comma k is 2h comma k, right? That's what it is, 2h comma k. Right. So let me give you a few exercises, and please do solve exercises from basic multivariable calculus. It is very well written book, and lot of exercises examples are there. And I'm also teaching from there. So I'll generally follow that book, and often will combine with Swiva. Right. So maybe I give few exercises. Exercises I decided to write. Here. Yeah. So exercises. Find the tangent to the graph of f xy is x square plus y square plus e to the power xy at 1 comma 0 comma 2. So this point lies in the graph. Okay, now you know how to find. Second, find the equation of the tangent plane to the hemisphere z equal to square root of 1 minus x square minus y square. And maybe 3, let me give you exercises from that book. Perhaps everybody then will look at the book. So exercises of basic multivariable calculus book. Page 132. So here there are some exercises. So do solve these things. So let us now look at the approximation. We had another interpretation of derivative, right? In for real line. So linear approximation. Right? So if you have function from R to R, and then what is the derivative? It's the approximation of f by a linear function, right? So suppose, let me repeat that. Suppose f to f R to R is differentiable at a, then of course you get this limit h tends to 0, f of a plus h minus f of a by h exist, and this is f prime a. So this means what we get is for every epsilon, well, let me write a little more. H tends to 0. H is in R now. This we have seen in analysis 2 class, that this is f of a plus h minus f a minus f prime a h uh, mod by h. Oh well, we don't need mod right here. This is equal to 0. Now this implies that for every epsilon, or this is if and only if, for every epsilon greater than 0, there exists delta greater than 0, such that mod of h less than delta implies mod of f of a plus h minus f of a minus f prime a h is lesser or equal to epsilon times mod h, right? So in particular, well, so in other words, what we have is as follows. So we want to remove h. We want to write this f of x minus f of a minus f prime a times x minus a, right? So here x minus a less than delta implies this less than epsilon times mod x minus a. Is it correct? Yeah? Is it correct? You have seen this,
Yes,
right?
just replacing a h with x minus a.
Right. There is no problem. What it means is when x is near a, you have this estimate, right? And this side you see you have better than continuity. You have epsilon times x minus a. So this means that f is approximated by fa plus f prime a x minus a near x equal to a. All right, and this is an affine map. This is an affine function. So you want to generalize this one also, and we could, right? So here this is the function we'll be looking at. So let us write it properly. Now, in case f from R2 to R, which we are looking at, we have the following: differentiable at x0 y0 means that for means that what means that limit h tends to 0, or let me put hk tends to 0, f of x0 plus h y0 plus k minus f of x0 y0 minus, now we know lambda, right, which is del f by del x at x0 y0 times h minus del f by del y at x0 y0 k, acting on k, this norm by norm of h comma k is 0. So this means while replacing this is in other words, well, this is fine, we'll write it. So this is if and only if for every epsilon greater than 0 there exists delta greater than 0 such that mod of f of mod of, let's say, similar thing, you just write similar thing, hk norm of hk less than delta implies norm of f of x plus h x naught plus h comma y naught plus k minus f of x naught y naught minus del f by del x x naught y naught h minus del f by del x x naught del f by del y x naught y naught k. This norm is less or equal to epsilon times norm of h comma k. All right. In other words, hk will be xy minus x naught y naught less than delta implies xy minus f of x naught y naught minus del f by del x x naught y naught at x minus x naught minus del f by del y minus del f by del y at x naught y naught y minus y naught less or equal to epsilon times norm of x minus x naught y minus y naught. Is this fine? See, the same thing. Just we now know what the lambda is, and we have replaced similar thing h to be x minus x naught and k to be y minus y naught. All right? Yeah. So this gives that f is approximated by the affine map xy goes to f of x naught y naught plus del f by del x naught y naught x minus x naught plus del f by del y x naught y naught y minus y naught and near x naught y naught. This is fine. So the same thing, the tangent space also gives an approximation to the graph, the surface. That is interesting point. Any question here? Yeah. So here page 1 and 133. Any question? Okay, so then I'll stop today.
Sir, what was the name of the author of multivariable calculus?
Okay, so the name of the author is Marsden, Tromba, and Weinstein. Okay, it is in the notes as well as it should be in the syllabus also. But yeah, I'll put it in Will learn also. The name of the book.